Think about the massive machines hanging off the wings of a commercial airliner. They are absolute marvels of modern engineering, packed with tens of thousands of intricate, rapidly spinning parts designed to lift hundreds of tons of metal into the sky safely. Now, compare that to a hypersonic missile like the BrahMos, designed to travel at Mach 5 or higher. If you look at its exterior, there are virtually no moving parts. The engine is essentially a smooth, hollow metal tube. This creates a massive paradox. Why does a low-speed commercial flight require thousands of complex spinning blades and interconnected gears, while the fastest weapons on Earth have almost zero moving parts inside their engines? To understand how an empty tube can outrun a modern, highly engineered turbofan, we first have to look at why commercial jets are burdened with so much internal machinery. Take a look at this turbofan engine. Those intricate, overlapping metal blades do the heavy lifting. When a jet is moving slowly, that giant fan aggressively pulls in the massive volume of air needed to keep it running. Once the air is inside, the engine runs on a continuous four-step cycle. It draws the air in through the fan, squeezes it down in a compressor to raise the pressure, mixes it with jet fuel, and ignites it in the combustion chamber. Before the hot exhaust leaves, it hits a rear turbine connected to the front compressor fan by a solid shaft. As exhaust rushes out, it spins the rear turbine, physically cranking the front fan to pull in more air. The entire engine is an interdependent loop. It requires constant, active mechanical movement just to breathe. This loop creates an immediate chicken and egg problem. If the front fan needs the rear turbine to spin, and the rear turbine needs the front fan to pull in air, how do you actually turn the engine on when the plane is parked? You have to add another engine. Hidden away in the tail of the plane is the APU, or Auxiliary Power Unit. It's a completely separate, smaller engine whose entire job is to kickstart the massive primary turbofans on the wings. And because those main turbofans need to be so massive to pull in enough air, they create external design problems. The engine cowlings often have to be physically flattened on the bottom just to guarantee they don't scrape the runway during a bumpy crosswind landing. Engineers even have to build heavy mechanical workarounds to slow the plane down. When landing, the engine housing slides open, deploying metal thrust reversers that block the rear exhaust and force it forward to act as a brake. Commercial aviation safety is achieved through an accumulation of mechanical complexity. Every possible scenario requires adding another physical part to control how air moves through the engine. Look at this photograph of US Airways Flight 1549 floating safely in the Hudson River. It proves an aircraft can survive the ultimate crisis, a scenario where a massive bird strike completely destroys the internal compressors, shutting down all primary engines simultaneously. Even with dead engines, the plane doesn't drop like a stone. Because of the physics of gliding, a commercial jet can travel roughly 3 miles forward for every 1 mile it drops in altitude. The immediate danger isn't falling, it's the total loss of internal electrical and hydraulic power. Without the engine spinning, the pilots lose the batteries and fluid pressure required to actually steer the plane. To solve this, engineers built the ultimate backup system, the Ram Air Turbine, or RAT. It's a small external propeller that drops from the belly of the plane. It has no engine of its own. It generates emergency electricity simply by spinning violently in the passing wind. At high speed, the force of the incoming wind alone replaces the need for internal combustion. The air itself provides the mechanical energy required to keep the aircraft's critical systems alive. Take that exact concept and push it to extremes. What happens to the air when you accelerate past the sound barrier? At Mach speeds, those complex spinning fan blades that commercial jets rely on to pull in air become a structural liability. They actually choke on the incoming supersonic wind, turning into a solid wall. The engineering solution for hypersonic missiles like Ramjets and Scramjets is to remove the problem entirely. You pull out the fans, the compressors, and the rear turbines. You rip out the entire internal ecosystem, leaving only an empty, specially shaped metal tube. This relies entirely on the ram effect. The extreme forward velocity of the missile rams air into the narrowing tube, creating a natural bottleneck. That bottleneck physically compresses the air to extreme pressures on its own. The system then injects fuel, sparks it, and highly energetic exhaust blasts out the back. There is one major drawback. Because a scramjet has 0 fans to suck in air from a standstill, you literally cannot start it on a runway. It requires a solid rocket booster to aggressively push it up to operational speed before the engine can even begin to breathe. By eliminating moving parts, engineers traded low-speed runway functionality for the ability to weaponize sheer atmospheric pressure at Mach 5. These two systems represent completely opposite approaches to moving through the sky. The commercial jet is a delicate, intricate ecosystem of fans, APUs, and backup turbines built to coax slow air into an engine. The scramjet is a brutal, empty tube. At hypersonic speeds, the physical velocity of the craft itself becomes the compressor. The speed is the machine. The evolution of ultimate speed in aviation was not achieved by inventing a better fan blade or a stronger turbine. In the quest for hypersonic flight, engineers didn't solve the problem by adding more power. They solved it by identifying every part they could afford to leave out.